I'd like to welcome everyone to our March Lunch and Learn for the Idaho section of the American Nuclear Society. I'd like to ask everyone who's connecting to make sure your cameras and your mics are muted as you're presenting. And feel free to ask questions on the chat window over on the right. And we'll get to those towards the end of the presentation. Got a really good talk for you. And I'm going to turn it over to Marty, the president of the local section. And he's going to introduce our guest speaker this month.
Thanks, Joe. Thanks, everybody, for being here. We really appreciate your attendance at this March installment of our Idaho section of the American Nuclear Society's Lunch and Learn program. Today, we're going to be listening and hearing great things about what's going on with renewing the Advanced Test Reactor from HansVogel, who's the Strategic Irradiation Capabilities, Division Director for the Advanced Test Reactor at the INL. Hans has had a lot of experience in the laboratory system. Before coming here to INL, he spent some time at the Oak Ridge National Laboratory as an operations manager in the Neutron Sciences Directorate at Oak Ridge, and was heavily involved in the Nuclear Systems Division activities for the ITER fusion project in France. He has also spent time at the Pacific Northwest National Laboratory as a senior project manager, where he was the nuclear and environmental safety and health manager. He's received a bachelor's degree in chemical engineering from the University of Nevada, Reno, a master's of science in environmental engineering from Washington State University. He was also a veteran of Desert Storm. We thank him for his service. He was in the U.S. Army. He retired from there at the rank of a captain, and after serving for 5 years, and received numerous military awards, including the Bronze Star. He's also been heavily involved in civic activities. Before coming here, he was on the Oak Ridge City Council and had to resign so he could come to the laboratory here in 2018 into his current position. Hans and his wife live here in town. They have 2 children, 2 sons. Evan is actually a firefighter for the city of Ammon, and their other son, Kyle, is stationed in New York on active duty in the U.S. Army. And so with that, Hans, we're going to turn the time over to you.
Great. No, I appreciate it. In terms of keeping it running for a heck of a long time, a lot longer than maybe some folks thought it would, but I think as folks that got a little more gray hair than I do even know that they built things back then with the intent that they would run for a heck of a long time. So with that, I'll go through my organization for strategic radiation capabilities at ATR. Focused on developing the business case that looked at Office of Nuclear Energy and Naval Reactor Program desire to keep running the thermal irradiation capability out to the year 2085. So we delivered a report on that this last year. And then also my organization does what we call plant health projects. So things that continue to sustain the existing reactor and that it runs as efficiently and best we can to meet our radiation needs. So with that, I'll give a little bit of background on test reactors, what makes ATR unique. And I think that by itself, when you look at the design, I always like this picture that's there, and you can see the cutaway for the gearbox support beams that are there for the safety drives, and that the fuel array that's there, the 40 elements that make up the serpentine. It's pretty cool. You don't see that anywhere else in the reactor world. So what we're doing to sustain the capabilities, again, the plant health program, And then what we're doing starting basically a month from today is the start of the core internal changeout, and what we'll do for the next 9 months to continue working on that. And then what we're looking forward to in terms of ATR's future. And then I'll go through any questions that folks have, and I hope to do that at the end. I can see the chat bar come up, but I looked to Joe or somebody else just to flag me and make sure we get all the questions answered at the end. So with that, the history of INL test reactors. So when you go in and look, there's a footnote on here looking at an IAEA website, but 103 high power reactors or greater than a megawatt thermal have operated worldwide, 6 under construction and 10 more planned. I know that I had the opportunity to go down and look at a part of an IAEA conference when I was down in Buenos Aires just over a year ago, and look at the Argentinian reactor they're building down there. It's pretty cool when you see how folks are going about doing those types of projects. 37 of them operational in the US, and the most powerful of these operate at the DOE lab. So I've had the benefit of working at the high flux isotope reactor. I've done nominally 2 tours there at HIFER, and now here at the Idaho National Laboratory in the Advanced Test Reactor. Preceding the ATR was the material test reactor. So that started as 20 megawatt thermal, went to 40, and then that operated from 52 to 1970, which is pretty cool for that reactor. And then ETR, 170 megawatt, 175 megawatt thermal, that operated at the test reactor area, and I'll show you that here on this next slide. But that went critical in 57, operated till 81. And then when you look at the next picture, you can actually see in this layout then the MTR, ETR reactor, these are the cooling towers, and then the ATR reactor over here. And this is looking basically southwest from the north at the test reactor area, or TRA area out there in 1970 vintage. So that's pretty cool. There's folks that I work with today out here whose fathers actually worked at the site and took the original ATR critical, or took ATR critical when it started up, and actually had experience with the other 2 reactors. So it's we do have that in our history, and with folks that have come out to the site and can talk about that. We do have people today that experience that, so it's kind of neat. All right, so in terms of ATR, it was created in response to fill something that the Atomic Energy Commission, the AEC, and the Navy looked at in terms of what they wanted to do, working for nuclear power plants for surface and submarine ships, and be able to do that. At the same time, when the AEC was doing this, the high flux isotope reactor was actually what they started with the AEC response, and the Navy said, well, wait a minute, we need one for our work, and that is what created the Advanced Test Reactor mission need. And so ATR actually works with the research capabilities and what they do for national security. We do work with NASA for space exploration with plutonium-238 production for the RTGs, and then university and research and industrial innovation, so support the user community there, and then medical isotope work. So we do cobalt-60 and produce the medical isotopes there. So 250 megawatt thermal capability, 1 times 10 to the 15th neutrons per square centimeter thermal flux, and it went critical in 67. So I'm not going to tell you how old I was then, but I was around. That said, in comparison, high flux isotope reactor runs at 2.5 times 10 to the 15th, but it only has 1 flux trap, not 9. So we'll go through that here as we progress. Okay, said before, ATR customers. So basically the big gorilla for us is the US Navy and the NNPP, or the Naval Nuclear Propulsion Program, needs for their testing for materials and fuels. So that's the big piece that we work with. Obviously, the Office of Nuclear Energy and the Department of Energy's Office of Science have a play. there as well. NE is our sponsor organization, so we appreciate them with their collaboration with Naval Reactors. NASA, as I mentioned, so they rely upon both the high flux isotope reactor in Oak Ridge and the advanced test reactor here at Idaho for their 238 production for their thermal generators. And then the medical and industrial needs and other special isotopes that can be produced with the irradiation capabilities we have. The university programs through the Nuclear Science User Facility, or NSUF. If you haven't looked at that, NSUF's got their website. You can find the other details about the other nuclear capabilities that are out there, HIFER and other reactor activities and hot cells that are available to use in the NSUF program. And then the industry, right now working with the National Reactor Innovation Center. So the Idaho National Laboratory has been designated as NRIC, and working then also with the Gateway for Accelerated Innovation and Nuclear Gain and initiatives that come out of there, and being able to utilize existing facilities or expanded capability in the future that we look forward to coming to the Idaho National Laboratory. And then the international customers. So we actually have an ICER certification, and working with the IAEA, and we collaborate, and that they are able to bring people out or share the abilities and some of the R&D that is done through that ICER relationship. Okay. All right, what makes ATR unique? As you can see, just the serpentine outline of the fuel, the 40 elements, and then the 9 void spaces that are there in terms of being able to put impile tubes or experiments in there. The rotating drums that we talk about that are there for the control, and so those outer shims. And then the radiation locations, either eye positions that are in the outer areas. And then the unique shape of the beryllium that's in here in terms of its moderator. So the whole cloverleaf design, the 9 flux traps, and then the other outer area irradiation capabilities that are there are really unique in terms of that configuration. My experience at HIFER's got 1. So HIFER would have just 1 central flux trap that's there, also surrounded by beryllium. And that's 1 gigantic big donut that's a lot different than having 8 sections like this. So very unique design, very unique in terms of its operation, and that the 4-foot high core region. So when you look at that and look across that entire stack that's there, if you looked at it in side view, that you end up with this nice even flux profile that's there. And that's, again, kind of unique for that. Independent power control. So there's actually what they call tilt. So we're actually able to control the power, let's say in the south, 20 megawatts, and be able to run 60 megawatts in the north. So you actually have a 3-to-1 power tilt across the axis of the core. Also unique. There aren't too many places you can go do that intentionally. And then individual experiment controls for the different experiment power loops. So we have 6 operating impile tubes today. Potential capability to go back up to 9, but that would take some pretty extensive work to get us back up to that, just because of margins and other activities that are going on. Okay. All right. So how do we typically operate? In terms of just going through a cycle, lasts about 6 to 8 weeks. So about 60 days of a normal irradiation cycle for that. Reactor refueling and experiment changeouts typically take an evolution for refuel about a month, 3 to 4 weeks. When we do that, what's also unique is that you've got the 40 elements that are there that are used in the serpentine array of the fuel, that we can use an element up to 3 to 4 times, depending on how we want to tailor the fuel and flux density. And so when you're doing a run, it's kind of different to think that you're not one and done with a fuel element, and that we actually store those out in the canal and then bring them back into use. And for each core, it is a different core safety analysis. So one could argue that every time we bring the reactor up, we've got a new core design for it. And it's really unique in terms of being able to do that and reuse the fuel. For the Naval Nuclear Propulsion Program, every third cycle we run what is called a Power Axial Locator Mechanism Run, or a PALM cycle. This allows the 2 experiments that are left in the reactor. We basically take all the other experiments out and move them into storage, and then run real high cycle time. So over the course of 7 to 10 days, depending on what we're doing with that, you could literally run an experiment in and out of the profile through the core in the high flux region 1,000 times in that time period. So again, unique in terms of what they're doing, but those are for power demand and propulsion, Navy nuclear propulsion program requirements. So PALM cycles, again, rather unique capability there. And then we'll run multiple cycles, obviously, throughout a fiscal or calendar year, and we track that in our ISOP, which is the operating plan, and project out about a 3-year window of what we're going to do for experiments and how we run. Okay. All right, so in terms of sustaining the capabilities, if you go back, I came to the laboratory in 2018. Preceding that, back in the 2012 to 2014 timeframe, the plant health program was initiated, and in that it was identifying that irradiation days, the ability to run the facility and give the highest number of irradiation days in a year, was starting to degrade. So if the desire was to run 180 days, you know, we'd be able to run about 140 because things weren't operating at the reliability and predictability that we were hoping for. So what happened at that time is they started the plant health program and the investments. And what we've developed now, as you see in the background, this investment strategy document we update every year, and it basically goes through the prioritized projects. So are we going to replace a motor? Are we going to replace a well? Or are we going to do something with a valve assembly or a different pump? What we do in terms of those projects and their prioritization to reduce the risk to not meeting our irradiation days. And so the execution of that is a DOE Office of Nuclear Energy, NE, and NR investment in the overall program. NE provides us funds that we go and put into that. We've, since 2016, been able to do over 100 million, and right now it's about $130 million of total scope. And we'll go through a couple of highlights in that we've worked on, including the CIC preps and things that we're going to talk about as well. So rather significant investment. It's kind of fun to watch folks that have been out here for many years that reflect that it's kind of nice to see this investment because it ensures that we are going to have the capability for much longer into the future, and that we're taking care of some things that folks have been concerned about in terms of just maintaining the facility and being able to run at the highest availability and predictability we can. The other thing we produce, not just a report of what we're doing, we started prepping what we call our brag book, okay? And so this is our accomplishments book, and that goes through and highlights the specific projects, the type of risk we've mitigated, the investment that was made to complete that, and gives our project managers some time to go and kind of pump up what they've done and literally brag about their successes. So that's been good. So give you an idea of what we've done. You look at some of these activities. So this is one of the original primary pump motors. And you don't get to see it after it's rewound and set up to go, but here it is in this new painted, and the shop at ATR took pride in doing that paint job on it. But being able to go back and rewind and bring a 50-year-old motor back up to nearly new condition and have it run again, or continue to run for many, many years is kind of neat. We talk about the 40-ton, 30-ton, the crane work. So you see some pictures here. This was one of the scariest days that I've worked at ATR, when you're actually taking the bridge portion of the crane down and replacing it with a new one. So this is the new one going in place with a lifting fixture tied to it, and the old one coming down. That's over the canal area, and sure as heck, we want to make sure that went to the deck in a very controlled fashion. And so you can see some of that in here in terms of, just the scale and get an idea of what we were working on with 30 and 40 ton crane in the high bay and canal area. But those are great. Now we've got very reliable cranes that'll take us not only through this core internal changeout, but probably the next 20 to 30 years of operations. So it's great. In terms of just normal infrastructure, so we're on wells to provide water out to the facility. And so you can see this is one of the old deep wells, M4, with a new one. So you can look at what the screen at the bottom of the well casing would look like compared to what was pulled out of there. And after 50 years of operation, you would expect it. But that's definitely something we wanted to make sure of, that we had a water supply that was reliable and available for us. So when you look at these deep well replacements for cooling water systems and overall infrastructure and potable water, they were important to get replaced. And so that was nice to be able to done. And then some things just like electrical systems, HVAC mods, RadCon systems. We actually have our radiation monitoring system that's been upgraded and brought up to more contemporary standards with some of the new equipment that's gone in. So these are all things we highlight in our brag book, and again, over $100 million worth of effort in the last 4 or 5 years. It's great to see. All right, that transitions then from kind of what we do on, I'd call it sort of routine maintenance, to once maybe in a career, but for some, there's a second or third opportunity to go through a core internal changeout. I've asked and not had anybody identify they were here 4 CICs ago, but a core internal changeout. So on average, when you see this timeline, ATR went critical back in '67, and they did the first CIC in '72, another one in '77, made it to '86, and then '94 and 2004. And here we are in 2021, next month, a month from today, start up this next core internal changeout. And that's based on talk about here a little bit of why they're needed. But we've gone 17 years since the last one. So we're knocking some dust off and have done a lot of preparedness in terms of operations and tooling and procedure reviews and getting prepared for this. But we had done 5 CICs up till now. And then takes place in 3 phases, and I'll go through the discrete phases here in a minute. But why are these needed? What do? We actually, once the reactor's scrammed, and I'll go through the details, we defuel it, take the experiments out, and we'll actually remove the top head. And then the top head of the reactor will come off, and then go through and systematically go in and take some of the infrastructure of the core internals out of there and replace them with new. But because we've got the large neutron flux, predominantly the beryllium and then the control systems that are in there through the control cylinders, we end up with swelling and cracking of the beryllium in there. We actually track that through an evaluation and take a look at when we think it would project out, that we would end up with enough swelling or cracking, and we monitor and visually inspect the beryllium and look at that to make sure it doesn't bind. So we don't have folks up there trying to put a fuel element into the grid, and because of the way the beryllium's gone in the last X number of years, that it won't fit as well, or it gets tight, or a control cylinder is binding or not moving freely. Those are the indicators that folks would look for and say, hey, it's time for CIC. We try to proactively look at that, and so again, monitor and evaluate when we think it would project to. And so in 2021, this, like I said, next month, we'll initiate a 9-month outage that will go in and replace things like the beryllium, like some of the control surfaces in there. And then it just also looks at potential for upgrades. We'll work through some of the other plant health projects during this time as well. Okay, so 3 phases, basically breaks down to removing the top head of the reactor and getting ready for working through the internals. So this is removal, taking out the gearbox and the outer shim control cylinders, the beryllium blocks, and getting everything out so you get what they call a clean vessel. And then look at the new components going in, and then shift once all of that's restacked and aligned. Then we go back and start to work on putting the top head back on and doing the impile tubes, and then go to nuclear testing and startup. So that's real high level. and I'll go into the details here on the next one. Okay, so in terms of phase one, that's where we actually remove the top head. So you can see over here, and we've got some pictures in there. Rather significant lift in making sure that that was a good reason why the 40-ton crane was back in there, because it's about, what is it, 36 tons, I think, if I'm recalling correctly, that's there. And then we remove all the fueled experiments and make sure that the in-pile tubes come out, the shield blocks, and get everything set up. And so when the top head comes off, it goes on a stand and sits on the reactor floor. And so you can see them going through, and this is a cask assembly on top, and removing experiments and getting things set up. So this whole area will start to come apart. Shield blocks will come off and do that. But we are shut down, depressurized, defueled, and then start moving things into the canal via this drop chute. So that's actually the tube. I can go back up, but it's how we transfer things without going in air from the reactor itself into the canal area. And then again, a lot of cask evolutions in terms of moving experiments around and getting that done. So then you're looking down at the top head itself, and these are shield blocks. So you've got 23 of these that move around and shield, and you can see the metallic surface under here. So this is the reactor top head itself and some of the ports and the port covers on them. And so as we move these blocks out, they'll be staged, and we're actually taking them outside of the facility, and about half of them. So figure, you know, what's half of an odd number, but about 12 of those will be taken over to another facility, actually sandblasted and repainted, and they'll be reinstalled when we go back into phase 3. But when you look at this, the shield blocks come off, and then we access the vessel head itself. And then you can see this, that's a rather significant lift, and you've got folks coming in, they're actually going to skirt the bottom of the vessel head itself. So 62,000 pound stainless lid. We lift that, put it on a stand, and we're actually going to do some work. So if you look down in this area, this is actually fuel grid support that's going to come off, but the underside of that's got what we call the top head closure plate. And we're actually going to replace that with a new top head closure plate that will have 8 additional holes in it that'll allow for other experiment capabilities to be used in the future. And that's tied to some other things with the Halden reactor shutting down and being able to take advantage of the ATR flux for doing future work in there. So, and then you'll see in this other picture, this is just basically a big tent. It's not the trampoline jump restraint that's there, but being able to put this tent area in some of the confinement interface that's there just to prevent contamination getting out of that area of the reactor vessel itself. Okay. All right, then we move into phase 2. So phase 2 goes in, like we said, removal of components within the reactor vessel itself. You can see this picture of operators looking over a port area down into the vessel and being able to get access to in-pile tubes and the cross arms that are there and get into taking other pieces of the reactor components out. So this platform's installed, and then they begin to further disassemble the core internals. And moving through, we've got, as was highlighted here in purple, are the control cylinders themselves. So being able to remove that, and then the gearboxes that turn these, they're up on top of the that assembly. Those gearboxes, is a picture of one, actually are the drives that turn those cylinders. They will go into these things affectionately called banana cans. And so these are shaped, they've got a little arch or bend to them. And those will actually be transferred out of the reactor vessel and into the canal through the drop chute. So that's going to be a tricky one because you're playing between 2 crane assemblies, one in the reactor high bay area and the other in the canal, and actually have to transfer that and move it from one area around the other without getting it stuck. So we've actually done some preliminary work on that and made sure that folks are proficient in getting that through. We took an empty banana can and played with it there, because having not done that for 17 years, it takes a little while. Okay, and then we do in-air transfers. So some of the equipment we can't fit through the drop chute, so we actually have to do it as in-air transfers. These are highly irradiated core components. And so when we actually do this, we evacuate the facility. There's a limited number of staff that are there to operate the crane. You can see some of these shielded areas that are there and the windows that we're able to shield. And then there's a contingent of folks that are outside the facility with a backup mounted winch to be able to move things if, heaven forbid, we were to lose power during that evolution or ran into a problem. But they do not fit through the top or the drop chute, and so we actually lift them out and then transfer them in air to the canal via the crane. And then the crane operators that are there, we actually evacuate the site and do that. And we're able to do that the way it's scheduled right now, basically through a Friday through a Sunday, which means there's limited staff around anyway, because our normal work week's a Monday through Thursday, a 4-10 schedule. So you see here the shielded booths and being able to work from those spaces, they actually can observe and keep the operators safe from the higher doses. Okay. So then the next thing we do is the reflector blocks and next shim housing. So the next shim is actually this tall aluminum component that's there in the central portion, and then the beryllium blocks. And so you can see the unique shape of these. The other thing we note in here is these are actually side cuts in the beryllium, and these are to allow for crack propagation to be limited. So you know, you run into a controlled cut here that the crack, if it were to start down in this section, that it wouldn't move beyond another area. And this is the nose piece that would be in near the impile tube itself. And so those are important to make sure that we have that, and that you know, we end up with no cracks or don't want a piece of that breaking off. Okay, so this is again is the biggest piece of making sure we start the CIC early, is that we don't want a control cylinder binding in these holes, or we don't want a piece of beryllium swelling or cracking such that we're unable to operate. Okay. All right, then we get into new component installation. So now everything's out of the reactor, we start building it back up. We're gonna do some vessel inspections. So this is just visual going in. We've already done some ultrasonic and played with some new scanners and had really good look at weld areas and questions about the integrity of the vessel. And it's pristine. It's the beauty of a stainless steel construction. But going in and doing these visual inspections, and we start building things back in. So the new neck shim housing, reflector, beryllium blocks go in, control cylinders, and start working things backwards from what we took apart. All this done through a lot of procedures and control points going through that. And then making sure everything aligns. So this is making sure things don't bind and get everything back to torque specs and to where the core itself is reconstructed. And then the shield blocks, the vessel head would be ready and reinstalled and get back to the end of that phase. And then we go back in phase 3 and get back inside the tank itself and start reinstalling the impile tubes. So then those and the experiments get loaded back in. We've got some welding to do for some of the cross arm pieces that tie into the side of the reactor vessel itself. And then once those installations are done, and I'm minimizing the amount of work, that's a huge effort. We have folks back in the tank again. You'll see some pictures here. We're using some new technology for us, but it's been out there in commercial forever, and doing the welds this time with new tooling. But everything's sealed up, tested, pressure tested, and then we're able to start up and get back into preps for getting the reactor back and doing nuclear testing. So when you look at this, we just actually got a new tube welder, right? So this orbital welder assembly, this is one of our welders actually looking and controlling the weld head. It's kind of cool. And I was out there when they were doing it, and the rep for these guys told us that this controller itself is set up off a Formula 1 race car steering wheel. That's what they used as a prototype to kind of lay that out. So I'm thinking, okay, that's That's pretty cool. But it'll allow us to actually, instead of doing hand welds, they're able to get this set up and do the orbital welder can knock these welds out and do it without somebody standing right up on it, which allows us to be more ALARA, right? And less radiation exposure. Okay, and then you can see here on this picture, folks being able to lower the in-pile tube assemblies back in and get the experiments set up and that part. And then when you're down in the bottom, so the bowels of the reactor and the sub-pile room, you can see where things protrude down the bottom. And this is something we have to go in and clean up in there as well. So we'll have the bottom of the in-pile tubes in the sub-pile room that we work through and making sure all these seals are tight and that we don't have any leaks. Okay. All right, so with that, I'm getting down to the end. We'll have completed that. It'll be a 9-month evolution going basically from April all the way through December. We're trying to finish up before Christmas holiday. And then we go into a phase of nuclear testing and making sure we understand the rebuild on the core profile. And it's exactly as we anticipated. We have customer demand for the irradiation capability. It's been identified well through 2040. If you read NNSA's strategic plan, they talk about thermal irradiation capability need at ATR all the way out through the year 2080. And I don't think I'll be operating or working out there that long, but I know we've got staff that have started that I think, you know, could potentially be out there for another 60 years. It'd be kind of fun. Okay, and then NE and NR, looking at this business case I mentioned in the front about how we keep going with the reactor itself or the capability out there and look at those needs, how we would meet current and future projected needs for radiation capabilities. And we're hoping that we get some direction to move down that path of looking at either a recapitalization of the existing reactor or the potential for a replacement reactor and get some direction from the federal government on path they want us to go in the next year or so. So we're anticipating that. So with that, I think, Joe, I get to the last slide. And you look back, this is a similar view to that earlier one, looking from the north back basically to the south. And you've got the reactor in the cooling tower here. And then our sister facility that's over here is a remote handled low-level waste facility that's just off to the other areas. So with that, I think I can answer questions, and I'm seeing the chat. And it looks like Elijah Cook said to everybody that loved the new primary pump. Yeah, they took the paint shop took a lot of pride in putting that together, and we're able to get that done. So, and then the question about how long does it take to depressurize? So basically about the first week as we enter into the scram of the reactor is where we start to do the depressurization, let the temperatures come down and settle, defuel the reactor and get things set up so we can start the next sets of evolution. So within a few days, we're down, depressurized, and defueled. So, and then Marty has got a question about in-pile tubes going back into the reactor, same ones. And we actually are replacing all but one of the in-pile tubes. So we've got 5 new ones going back in. And I guess the question, fluence limits. So we did have a failure. The 2 Delta in-pile tube actually had a failure not too long ago. And that one has not reached anywhere near its time in the reactor. And so we'll reuse that, but everything else is getting replaced with new. Next one I see there is Vince asking, is any computational support needed for ATR? Yeah, we do. There's actually an entire group that does nothing but the modeling for the reactor cores themselves. And then the Nuclear Science and Technology Directorate, when they do experiments, they do all kinds of computational models. And then there's the adjoining facility, which is the ATR critical facility, and do experiment. We'll do flux runs in there, take the data from that and computationally evaluate what we've got when we will put it into the main reactor, into the ATR itself, in terms of what influence it would have on the flux profile and temperature and pressure type of calculations. So definitely a lot of computational work that goes in on the back end or front end of that. Okay, and then Marty asked, big changes to the ESA or the SAR from CIC? No, actually not, because we're really not changing the configuration of the core itself relative to the SAR or the safety analysis that's there for the experiments. So the intent is to put it back the way we found it, right? So complete it and have it operating back so that the core itself operates as it did before. Amy Lentz, so I see Amy on there. ATR older reactor, has there been challenge in finding replacement materials? Absolutely. That's a challenge across the Department of Energy for some facilities like this. HIFER has it too. We actually have got, that's why I said we have the potential to run 9 impile tubes, but in the cubicle area, we've got one that we've actually used and cannibalized some of the equipment there because it's kind of hard to find. So it would take us some time to be able to rebuild and replace parts like that. Okay. Mark DeHart. So want to say anything about computational methods to be employed after CIC? I guess I can. It's not really my area. Pardon me for a second. But the MC21 modeling, I think, is what Mark's referring to, and collaborating with Office of Naval Reactors and the folks up there with their computational platform with MC21, and being able to potentially minimize some of the computational needs or experiment or ATRC runs for some of the NR experiments, and depending on the type of experiment that others would bring using MC21 for those as well. So Mark, give me a thumbs up or another one if that answers that question. I see Steve Laughlin. So the plant health program improved ATR performance in terms of actual versus scheduled or operating days. Absolutely has. In particular, we like to highlight the availability of the ATR critical facility. One of the big projects we did, and I know that Joe could probably flash that up, is what we did for the control console and put in a new entire control panel for ATRC. That was one of our biggest downtime contributors in plant health, was the fact that would keep us down in the ATRC runs. And then other places, when you talk about motors, we've talked about the deep wells, being able to have that as the backup. There is definitely an overall improvement in our reliability and predictability and risk reduction relative to those. So yeah, it's paid off. The 100 million has been a good investment. We got plenty more to go. Let's see, Braden. So talk about building a new VTR or overhaul. Were reasons for overhaul chosen over a rebuild? No. So in terms of a potential for replacement ATR, vice a recap or refurbishment of the existing ATR, that decision's not been made. We made a pitch to the department that if you want to be able to provide this type of capability out till the year 2080, 2085, that it would be prudent to consider a replacement reactor. But we also gave them the scenarios for doing recapitalization of the existing reactor, and that decision's not been made yet. So we're hoping that the department can give us some direction, like I said, maybe in the next year, and that we'll start down that path. At that point, you're talking a rather significant, or the Department of Energy's got an order on capital projects. It's well over $100 million worth of effort, so that would put us into that DOE Order 413 3B space, and we would evaluate there on an analysis of alternatives. So formally generate an analysis that would allow the department to make a formal designation of the path it wants to go down. So no decision yet on that. Mark, thank you. Okay, good. Answered that question on MC21. Sal Mascarenas. Sal, haven't seen you for a while. So yep, ATR, I think that's it. VTR is the versatile test reactor, a fast neutron reactor, and VTR is still moving through its project phases, completed its analysis of alternatives, and is waiting on the department to continue to move forward with that project and make some decisions on its timing and funding profile and path forward for that. So, Sal, I think I got that question there. Marty, another question. How much longer can the reactor vessel last under current op tempo? So that was the fun part, right? When we actually look at it, it's a stainless construction. Analysis looked at that based on what they were seeing influence and impact to the reactor vessel itself, that it could go potentially 300 years. So we're well into the early parts of that, with only operating about 53, 54 years for the reactor. But we went in and did some weld verification and looked at that, and it reaffirmed where we thought we were for the vessel itself. So it's in really super good shape. I'm gonna take a drink of water. And yes, I did pick my cup to match the color of my shirt today. But that the vessel itself, its integrity is very pristine, and the commercial folks we used, IIA, that came in and inspected it, said that it was cleaner and in better shape than a lot of the commercial work that they went out and reviewed. So, Steve, curious about what dose rates are expected in the in-air transfer of the beryllium block. So, I don't have that off the top of my head. I know that with the shielding and time that we use in terms of the transfers themselves, folks don't max out on their annual dose exposure. It's a high field, and that's why we minimize the amount of people that are there. But within the shielded area, excuse me, and the time that they're there, they actually don't max out on their annual dose. So we don't, quote unquote, burn them out for the entire outage itself. They're able to continue to support. So it's high, but it's not that that we can't deal with that. So let's see. Sal, yes, meant ATR, okay. And then Karen. So does ATR still have some analog controls versus digital? Any implications for this in this year's CIC? Actually, there's a lot of analog that's there. We've gone through and done a lot of work on relay replacements in the relay cabinets themselves. Well over 500 of the relays that we replaced in the last year and a half. So we've got a lot of mechanical interfaces. ATRC, when we put the new control console in, they're solid state, excuse me, but everything basically interacts with the existing analog interfaces that are in there. So most of those control systems are still analog based. INC upgrades, asked by Marty. Definitely, it's ongoing. So we've actually put in new backbone infrastructure with some of the computing interfaces or computer interfaces that are there. And that's been part of plant health. So it's not just specific to INC, but we are trying to do better in terms of coming a little closer to state of the art with some of the computing interfaces for safety and control systems. So it's an ongoing process of changing those out. All right, so let's see. So it looks like Ken, what happens to the change-out components? Is there a sampling plan for post-irradiation examination? So some of the components, we've actually got stuff going back, excuse me, I swallowed a bug today or something, back to the first CIC. So there's still some materials that are in the canal stored. There's not a big effort for doing PIE. There was, as I mentioned, one of the impile tubes had a failure. In the last few years, there was a section cut out and there was some PIE done on that, but generally, no, there's not a big PIE activity that goes with that. So, and I think that answers that. Sean, thank you. 18 millirem from the last CIC beryllium transfer. I didn't have that. I know that in those shielded spaces that it is pretty low. So thank you, Sean, for that. And that's it. I think I got everything in the question queue, and I only got one correction from my boss. So thank you, Sean.
Thank you, Hans. We really do appreciate you being with us today. Anyone have any other questions before we wrap this up? Well, Sean, I think you set a new record for attendance at one of these meetings. I saw a maximum of 110 in the presentation, so more than we could ever do face to face, because we usually don't have the facilities to do that. So thank you so much. Appreciate it. Very interesting. And I'm glad to hear that the ATR's got a long and potentially excellent and successful future here at the laboratory.
Thanks, Marty.
We'll be posting the video from this meeting and the slides on the IANS website for those who couldn't make it. I know we had a lot of folks that you responded tentatively but couldn't attend. So.
And then, Joe, you'll get that word out on the link to that.
Will do.
Very good. All right. Well, thank you so much, everybody. Appreciate you being part of our meeting. Our future meetings, it looks like we've got the next one will be Terry Erishman in April. The date hasn't been set yet, but she's over the Citizen Advisory Board for the laboratory. And then we have Mark Peters scheduled for May, and he'll talk about whatever he feels like talking about, actually, reminiscing about his times here or the future of what's going on at Battelle. With relation to the DOE and the laboratory system. So be watching for those advertisements for those. And thank you all for being here. We appreciate it very much. Bye now.